I'd like to introduce you to Francesca McFadden. She's worked on modeling, simulation, and analysis to evaluate system architectures at Johns Hopkins Applied Physics Laboratory since 2010. She's earned a bachelor's in computational mathematics with an additional major in statistics from Carnegie Mellon University. She has a master's degree in applied mathematics from North Carolina State University, and she's currently pursuing a doctoral degree at University of Maryland, Baltimore County. All right.
Thanks so much for the introduction. Before I get started, I want to note this work was done as independent study at UMBC with Dr. Matthias Dauber. So first, let's go over what does it mean ensemble learning methods. So with ensemble learning methods, what's happening is that you have multiple classifiers. They each get a decision, such as an input image. Each classifier might say, hey, this is a dog, this is a cat, right? So with each of those input classifiers, you'll take the combined or the amalgate of those classifiers, and you'll use that to get one prediction. So when you have an ensemble, which is what the multiple classifiers is called, you hopefully will have classifiers that have diverse or various assumptions. So what do we mean by that? What we mean by that is that they have different train data that they use. There might be some changes in the features that were used, and there therefore will be different decision boundaries as a result. You might even have cases where potentially they had different class outcomes, but those class outcomes could be mapped to the overall class of the ensemble. And what we're looking at is when you have voting schemes that you use to weigh those individual classifiers' outcomes to get that combined, fused, or selected prediction of class. And with the voting schemes in general, they often use the posterior confidence to be able to figure out how to weigh the results or how they should select amongst them. And as I said, it really helps to have complementary ways of designing those classifiers. And that's a huge advantage when you want to get that ensemble, but there's not really good ways to exploit that complementary nature of the different classifiers in a simple approach that's human understandable. So the approach that's actually taken, which I'll go into more details on the next slide on, is that you use a neural network. You'll have a meta classifier that comes out of that neural network. And that is the attempt to be able to learn the complementary behavior of the individual classifiers to get the amalgate decision. And the problem with that is what it does is it causes you to lose explainability to end users. You have less transparency in how each of the individual classifiers was used to get the final decision. So what I'm trying to find is a middle ground between these, where you are able to pull the ensemble in, you're able to still be able to exploit where there's complementary design in them, but it's still transparent to end users of how it was surmised, how the result was surmised. So first, I'm going to go into what simple voting schemes in case anybody didn't know what I was talking about on the last slide. So I would like you to concentrate on the gray box here. And in the gray box, just for simplicity, I'm just making an example with two classifiers. So if we have an example with two classifiers, there's multiple simple approaches we can use to get an ensemble. One of the options is we can end up taking the different predicted confidence that comes out of the two classifiers, and then we can do an average of the outcomes. And in this case, with the average of the classifier confidences, we might get class B is the final prediction because the average is higher for class B. There's other approaches where you might do a weighted average. And when you're doing a weighted average, what you're doing is you might have some labeled training set where you'll be able to understand the performance of the individual classifiers. And from there, you can use that to weight their averages. The next option is you could also just say which one had the highest overall confidence of any of the classes. And for this one, if you look at any of them, the highest obviously is the 0.7 here. But sometimes you want to filter which of the classifiers you're using. And that's going to be more akin to what we're going to go over later. And when you want to filter them, you might have some reason that you have a threshold by which if the predicted confidence is not above that threshold, then you would end up discounting a classifier. So in this case, we have that, and I apologize, and there's some weird highlighting happening. Let me try to get rid of that. The acceptance threshold on classifier 1 is 0.5. So class A obviously has a value above that 0.5. So we'll count that one. But class 2 had an acceptance threshold of 0.8. The confidence was never above 0.8 for either of the possible class outcomes. So that one doesn't get to count. We filtered it out. So effectively, there's only one that gets to vote, and you only get class A out of that. We might also have some reason that we trust one of the classifiers more. So when they disagree, we might say, when they disagree, we're going to side with one of them. We're going to have one that we think is a better source of prediction. And in this case, we might say that we've already predetermined that we know classifier 1's a better performer, and so we're going to stick to its outcome when they disagree, and so we'll just have class A as outcome. Those are all very simple. Everybody here understands how each one of the classifiers was used, but that's not what's done in practice. What's done in practice is these more advanced approaches, these networked approaches, where you'll have neural networks, where you're doing bagging or bootstrapping on the inputs, and you're using a meta classifier that has hidden layers or embedded layers to be able to come up with the ensemble's decision. And when that is done, you have lost transparency. You have made it so it's not as obvious where the decisions come from, which of the classifiers was preferred. And that's really important because one of these classifiers might be built off of really good training data that came from great measurements. And one of them, you might have some transfer learning approach going on. So you could have different approaches that were used in design of the classifiers, causing you to maybe have one that you might want to rely on more than the others. So what we're trying to do is figure out how we can bring transparency back into how these are combined. So when you build the individual classifiers, as I said, there's going to be different training data that you've used. In the training data that you've used, there could be different distributions of the training data. There could even be cases where you have total different class representations or differences in class imbalance from what was used in the train set. And you can even have different features where some of the features might introduce potential cause for prediction error, where you have potential overlaps in the prediction in the feature space. And so what ends up happening if you're just using model confidence alone, where you are basically masking all of these underlying uncertainties, is you're not able to really pull out where there might be better performance because one of these classifiers is better able to represent the input in the training data it had. And so what we're attempting to do is look where we can be able to measure when a model could be more competent to predict on a input. And in fact, there's been a lot of research on this topic. The model that I tend to use on this topic for measuring model competence is one that came from the 2019 NeurIPS from Rajendran and Levine. And that one is called ALICE. ALICE stands for Accurate Layer-Wise Interpretable Competence Estimation. And it's a product of 3 factors that includes distributional model and data uncertainty. So you're looking at distances from the input data to the trained data set that you had. It also does weigh in the confidence, so that is part of the scale. What ends up resulting is a score, or an ALICE score or competence score between 0 and 1. The one caution whenever this is used or other techniques are used is there's often some underlying thresholds that must be set by subject matter experts on the data types or on the application. So I'll show you what that process looks like of figuring out those thresholds later. But the idea here is that if we use a score like this, we have a certain threshold, and above that threshold, we say that the model is more competent to perform for that input, we're able to understand that might be a preferred model to use. It might be, though, we have a classifier with an ensemble with many classifiers, and we might have a few different of our classifiers get better performance or higher competence scores in that area. So under the approach, we're going to augment the simple schema that we had earlier, and we're going to introduce how we would include these competence scores. So the purpose here is that if you have consensus, obviously everybody agrees, right? All the classifiers agree. There's nothing different, right? It's when you have non-consensus, then we introduce just an additional step to our approach. And in that additional step, we look to see, as I show here on the right, what we're looking at is that the competence score classifier 1 did not have a result that met threshold, whereas classifier 2 did. So in this case, we filter out the vote for classifier 1, and we only allow classifier 2 to vote. And if we have it so that multiple of them satisfy the competence score threshold or neither of them, then we fall back to the traditional simple approaches. Either way, with this approach, we're able to clearly be able to tell the end user which of the classifiers was used in the decision and why. So as an example, for today, what I ended up going with was the diabetes health indicator data set. If anyone's not familiar, that is an annual survey that the CDC does. And in that annual survey, they have in it different risk factors for diabetes, health indicators, and just to go into a few of them, things like whether the person smokes, whether they have difficulty walking, body mass index, etc. So in that annual survey, a few 100,000 people from across all 50 states and US territories are interviewed. And they'll also look at, after that survey, they also have indicators of whether they are pre-diabetic or diabetic, or whether they are non-diabetic or just have gestational diabetes, which means only during pregnancy. And the one thing with this data set I want to note is that I use the clean version on Kaggle. And the other thing I want to note is that overall, there's 21 features in the data set. These features include categorical features as well. And the reason I want to go with this data set versus a data set that might be a cleaner story if it only had numeric entries is I want to show that this approach could also work for data sets where you had multiple categorical variables. So if we look on the right, there's an inset table. And in that inset table, I'm looking at the Pearson's correlation of the top 10 features with the diabetes indicator. And then I subset that list down to 5, and that's what I'm showing in the core plot, the correlation plot here. And I overlaid that for some of the binary features with the values. One of the important things that audience will note is that there's a much higher number of the survey that does not have diabetes. So I use simple sampling approaches, but I could do better sampling approaches for follow-on investigations if I was really wanting to pursue this data set to make it so that we had a better balance between those two. But for now, I just did a simple approach. So as you'll see later, we'll end up getting better performance in the classifiers when we have the no diabetes cases. Okay. So I built 2 classifiers, and these are both random forest classifiers that each had 100 trees. To build them, I did 2 individual uniform samples of 60% of the data. And for the classifier 1, I used the top 10 features. And for classifier 2, I used the top 5, so the ones that were plotted. And then what I'm showing there is the confusion matrix between the two. What we see here is with the top 5 features, the classifier 2 has better performance. We have better performance prediction of non-diabetes when non-diabetic, and same thing diabetes when diabetes, and also type 1, type 2 errors. The other thing to note is that with these 2 random draws for 60% of the data, I was still able to reserve 30% of the data as a test data set so that I could show you results. So now this is where we come down to the competence scores. So I said that was part of the approach. So to understand appropriate thresholds for the competence scores, I did a subset of the training data set, did 5,000 points, and I used that to determine what appropriate thresholds were to use in the ensemble. And what we see here is that largely for the classifier 1, we have the competence score is going with the classifier confidence. We have a minor drop off in one of the higher bins for the competence score, only due to lack of representation in that bin, and I ended up using a 0.5 threshold for that case. For the classifier 2, it wasn't as clean a story. If we plot versus the counts as multimodal, and for that one, I did a lower classifier confidence because of the higher heat map where we had lower confidence scores mapping to the lower classifier confidence. Sorry. Meant to stay on the slide. So we have 2 different thresholds for each of these classifiers. The classifier 2 in general does have a little bit better performance, which we'll see, and we saw in the last chart. So now the first thing is, as I said, if there's consensus, then what the approach I'm talking about doesn't really matter. So the first thing I checked is how often do we have consensus? And for over 94% of the cases, we ended up having consensus across the 2. So when we have consensus, as you would expect, there's better performance, right? So compared to the 2 classifiers alone, if we look at the cases where there's consensus, we have overall better performance if we look at the traditional metrics. So now what we're really worried about, though, is when we don't have consensus. So the question is, though, if we don't have consensus, is one of them right? Well, it's kind of easy for this case because there's only 2 classes, right? So it's either your diabetes or no diabetes. So one of them is going to be right for this case. So what that means, though, is that when there is non-consensus, there's an opportunity for us to get an ensemble that's right. Doesn't mean we're going to filter the correct classifier all the time, but we have a chance. So what I ended up doing was looking at a case where on the top right, for the results, I did a simple approach where I just looked at the highest confidence method, and for the highest confidence method, which we have here, again, this is for the test data set. What we see is we have performance 80% for the true negative rate and 96.3 for the true positive rate. Okay. However, when we introduce the approach I laid out earlier, where we incorporate the competence score, what we see is that we actually get slightly better performance, as we would hope. It could actually be even better if it was a numeric feature set only, because it's a more clear line between where the thresholds are. Is a lot easier to do. But I purposely wanted to show a case where there's a more common type of data set that we'd have, where we do have actually binary features, categorical features, etc., integer features. And so even still, for this data set, we were able to get better performance. it's slightly better. And one of the things that I'm doing now is looking at other data sets, such as the more classic ones as Fisher Iris, et cetera, to show where we can even get more drastic differences in performance. And the important thing with this is for every single one of those decisions, I was able to log this classifier was used or this classifier was filtered. So it was very obvious if we had a recommender system that we could show an end user classifier 1 used, classifier or not used, classifier 2 used, not used, what was their decisions, and then the person can see that. So there's transparency to the end user for human machine teaming applications. So as I said, we are able to demonstrate the approach. We are able to get performance, the promise that we hoped for. Obviously, we want to look at more data sets to show where we can get even better performance. The other important thing that, yes, got the time, that I want to know is that another concern one might have with this kind of approach is, can it be done in real time? So last October, I briefed at the SciEM Mathematics and Data Science Conference, and I showed how you could get these scores at the speed of decision. So it is possible to do that. There's nothing prohibits that from this kind of approach. And the other important thing is, as I already said, that we've showed an approach that's much more explainable to end users, more transparent to end users than the common neural net or network learning approaches. And appropriate visualizations could be used to fully aid in that. One other note I want to make is that I use MATLAB as the environment to process the data, to create the tree bagger models or in forest, to generate plots, confusion matrix, etc. With that, I'm almost out of time, so thank you. Yeah.
Thanks for the talk.
Yeah.
I'm curious if it's possible to incorporate favorability to types of errors in your in this competence score. So for instance, in the diabetes example, if you wanted to lean more towards making, I guess, false positives, because maybe you don't want to miss someone who has diabetes, but you say they don't. Is it possible that in some way to incorporate that preference in the
So one way that might be able to be introduced, which I'm kind of, and I haven't actually considered that problem, but I think it's a great idea. But you do look and see the distance of the prediction from each of the label inputs. So there's potentially a way to change the different thresholds that you're using if you end up having a case where you're not able to achieve threshold, where you have a different, like the opposite class prediction. Cool. Yeah. Any other questions or online? I'm sorry, I don't see the chat if there's some. Oh, okay.
I have a question.
Yeah.
Much less expert question. I'm not quite sure I follow, like on slide 9, I think it was. Why you would if you have one model that you're more confident in than the other one, why does it improve adding the other one in? Or is it because you're using multiple models and multiple scenarios?
It's because there's going to be differences in the training data that was used for each one of them. There could even be difference in the features that was used. And so inherently, when you have the different models, you end up actually getting a more robust solution. This is just part of ensemble methods in general. It's not even just for this approach. Yeah. Basically the diversity in the different classifiers actually it makes your overall solution better. It's just, you need to be able to figure out how to exploit it. Yeah.
Thanks. I'm wondering if you tried at all using a neural network as an ingestion layer, and then using these classical methods as a second layer of the stack process the outputs from.
So actually, I think that's, it's funny you should say that. So in one hand, I want to be able to make sure to use have the ability to show transparent solutions, right, to the end user. But on the other hand, actually, you could do something like that. So there's approaches where you have the outcomes of one classifier is fed into the other, and that I actually have listed here. But in those approaches, you might not consider that one classifier's decision. You might skip that one and go on to the next classifier if you had several classifiers. So it is possible you can actually fold this kind of approach even into the neural net approaches for meta classifiers. Yes. And you would still know, like, hey, why was this class versus that one? It's just you do still lose because most of the time that's not actually in practice what you're going to actually end up using is the meta classifier. So what could end up happening is you might have done that in the process of creating it, but you'll lose that transparency ultimately. Like when the person is actually going to use the meta classifier.
You look at, I imagine if two models are built very similarly and on the same training data, that there's not a lot of usefulness in deciding which one to vote for. But if they're built very differently, then it's a lot more useful. Did you look at thresholds for how different they have to work in order
Yes.
for this to be a useful
Yes.
exercise?
Yes, I did. So at first, when I built the two classifiers, I actually did them both with the same features, and it wasn't as transparent, like it wasn't as obvious of the trends. So even with this one, where it's the same data set, different polls of that data set, and different features, like there's some overlap. I was able to show the differences. But if they're very similar, obviously, like you don't have that variety in them. You'll still likely to get some improvement, but it might not be as drastic. So even for this case, I could have chose completely different feature sets and I would have been able to show something more drastic.